Hello friends, I welcome you all to this session on power plant engineering. So in this particular lecture, we'll try to understand the impact of boiler and condenser pressure on the Rankine cycle. Now, this is your Rankine cycle. So let's say this is the value of temperature beyond which we cannot go. Why? Because there is a metallurgical constraint that if the steam temperature go beyond, let's say, 560 or 570 or 600 depending on the material of the turbine blades, then there is a possibility that creep can happen there. So to prevent creep to happen, we set the limit of the temperature beyond which the temperature of the steam at the turbine inlet doesn't go. So let us understand the impact of the boiler pressure. So if I increase the boiler pressure from this value to this value, what has happened? So, two things you can observe. The first, the dryness fraction, if this is point number 1, this is point number 2, this is 2 prime, this is 3, this is 4, this is 4 prime, and this is 1 prime, let's say, then you can observe that this is x prime, let's say, that the dryness fraction at the exit of turbine will reduce. So as I increase the boiler pressure, what will happen? The quality of steam at the exit of turbine deteriorates. That means the dryness fraction at point number, this is let's say 2 prime, will reduce, or I can say 2 prime will be less than x. So here you can see that with the reduction in the dryness fraction, what will happen? There will be more moisture at the exit of turbine, and there are more chances that the uh, turbine blade will get eroded. So there will be that means here the erosion means the particles or the water droplet will act as a bullet, because at the exit there will be huge velocity, and that velocity, so those water droplets when impinges on the blade with that high velocity, they will create damage to the blade. So what has been said that at the exit dryness fraction should not be less than 0.85. It should be more than 0.85 to 0.87. So if it is more than, let's say, 0.87, then we are on the safer side, otherwise not. So with the increase in the boiler pressure, what has happened? The dryness fraction at the exit of the blade reduces. Also, we can also see that the work output W of the turbine will increase, and due to this I will be getting more work from the turbine, and as well as the heat input will also get changes, it will also be affected by this. But the major thing which you should be concerned about is the dryness fraction at the exit of the blade. So beyond a certain limit, I cannot go. Beyond a certain limit of pressure, if I go with single turbine, then there will be chances that the erosion of the blade will happen. Now, what is the impact of condenser pressure? So, if this is my Rankine cycle, 1, 2, 3, 4, and if I reduce the condenser pressure, so if I come here, let's say, this is my new condenser pressure, then expansion will lead to this 2 prime. Okay, then this will be 3 prime, this will be 4 prime. Now what has happened? So again, if you look here, this is the dryness fraction here at 2, and this is the dryness fraction at x2 prime. Again, if I reduce the condenser pressure, the dryness fraction at the exit of the turbine will reduce. And again, there are chances of blade erosion there. On the side of work, I will be getting more work. But there is a problem. Boiler pressure I am having in my hand, I can control it. But when it comes to condenser, the atmosphere surrounding will impose constraint that I cannot go beyond this below this particular pressure. Okay, though it is more effective in comparison to increasing the boiler pressure, but the atmosphere imposes a constraint. So in general, if I tell you that with the increase in boiler pressure, you are getting more work from the turbine, though you have to supply more work to the pump also, but that is very minimal in comparison to the turbine work output. But the major problem or the drawback is that the quality of the steam at the exit of turbine deteriorates. This has to be taken into care. Also, if I reduce the condenser pressure, again I will be getting more work, but at the cost of dryness fraction at the exit of turbine. So whatsoever may be the case, we have to be assured that the exit dryness fraction should not fall below 0.87. So this should be clear to us. So let us head to the Excel and see exactly what is happening. So now let's say my boiler pressure is right now 150 bar. So with this I am getting, you should be focusing on the net work output. Let me highlight it, this, as well as the dryness fraction. So these are the 2 points you should be focusing on. So first what I will do is I will increase the boiler pressure. So from 15 right now, if I increase the boiler pressure from, let's say, 150 bar to 180 bar, then you can see that the work output. So previously, so let me draw this. Let me do what? Let me make a table here. I'll increase it from, let's say, 100 bars, and then it is 150 bar, then it is 180 bar, and that's it. And here I will be writing my network output, network, and the dryness fraction at the exit of turbine. Okay, so if I am at let's say 100 bar, then the work output was 1040 and the dryness fraction was 0.9. So if I move from this 100 bar to 150 bar, then the work output will be 1071 and the dryness fraction will be 0.86. So if the work increases, if the pressure increases from 150 bar to 180 bar, then the work output will be 1078 and the dryness fraction has deteriorated to 0.84. Now you can see. So if you try to plot these, though we have only less points. Oh, what I have plotted? Series 1, series 2? No, I should be plotting. Still it is coming like this only. Why? So let us do one thing. Let us insert a chart here. Again it has been selected, I think. So it doesn't matter. We will select data. We'll remove this. Remove, and we'll add new, and boiler pressure, and then work output. So this is the work output. Okay, and then we will add another. So again boiler pressure on the x-axis and the dryness fraction on the y-axis. Okay, okay, okay. Then what we'll do is we will make it secondary axis so that you can understand this better. Now you can see that if okay, let us format this also. Let us start with 10,000. Okay, now what can you see? That this particular one, this orange line, is representative of dryness fraction. So as I increase the boiler pressure, the dryness fraction continuously reduces, and this is dangerous. Whereas if I increase the boiler pressure, what is happening? Work output is increasing, but it is increasing, then it is reducing. So basically it is increasing at the reducing rate. So we are not getting that much benefit in terms of work output also as I increase the boiler beyond a certain boiler pressure beyond a certain limit. So this has to be kept in mind while increasing the pressure of the boiler, because we are getting work output more, okay, but we are not getting that much work output in comparison to what we have increased the pressure, whereas the dryness fraction is reducing like anything. So this is the impact of boiler pressure on the uh, work output. And you can also see it from here that the dryness fraction, it has, the line has moved very inside. So this is a very dangerous thing. Now let us do the same exercise, but now this time for the condenser pressure. So this is not boiler, this is condenser, and let us keep it as 15 150 bar, and let us increase the condenser pressure from 100. So when it is 100 kilopascal means 1 bar. So then we'll go to, let's say, 300 and then 500. So when 100 is there, the dryness fraction was 0.86 and the work output was 1071. Now if I, so I was supposed to reduce it, no? Okay, let us do it other way around, 500, 300, 100. So when the condenser pressure was 500, the work output was 813 and the dryness fraction was 0.94, very good dryness fraction. When the condenser pressure reduces to 300, the work output increases to 900 and the dryness fraction reduces to 0.911. And when this becomes 100, the work output increases to 1071 and the dryness fraction becomes 0.86. Now that is what happens. So if I copy this figure and let us take this pressure and this work output, okay. Now what about series 2, where it has gone? Select data. So series 2, edit, x-axis was this, so now this will be my x-axis. Then comes the y-axis was dryness fraction, so this will be my y-axis, okay, and okay. Where it has gone, I'm not able to see it, so let us reconfigure it. Access options from 0, so this is the one. Now what you can see is that when with the, this is what, this is work output, okay. So work output is increasing more fast in comparison, though it is reducing, but it is reducing in at a rate which is lesser than what the condenser pressure was with the boiler pressure, whereas the dryness fraction, you can see it deteriorates. So the catch from both the analysis says that if I increase the boiler pressure or if I reduce the condenser pressure, in both the cases I will be getting higher work, but the work which I will be getting is not that sharp, not that fastly increasing in comparison to what was expected. And at the same time, whenever there is a reduction in the boiler pressure, you can see that the dryness fraction decreases, and this is a very serious thing. So you should always remember that with the boiler pressure, work output always increases. If I increase the boiler pressure, work output increases, but the dryness fraction reduces. Whereas if I reduce the condenser pressure, so the boiler, so the work output will increase, and at the same time, dryness fraction will reduce. And we have to keep the dryness fraction at the turbine exit not less than 0.87. So that's this you should understand. So in this lecture, till this point only, in the next lecture we will be learning about that, okay, so far we have done it, no problem, but how to increase the boiler pressure but at the same time limit the dryness fraction at the exit of this particular turbine, and this is basically done with the help of reheating. So we will be learning about reheating in the next lecture. Thank you very much for watching it. Take care.